Okay, this video is about running a capillary flash chromatography column. This is the smallest size preparatory column that one typically runs in an organic synthesis lab. A pipette column can handle between, say, 1 or 2 milligrams all the way up to, at most, 70 to 80 milligrams of a compound. As its name implies, this is going to be a pipette column. We're going to build the column in a Pasteur pipette. In order that the silica gel doesn't just drain through the pipette, what we need to do first is we need to get a small plug of cotton jammed into the end. So you get a small plug of cotton, a little cotton ball, you just rip it down to a point where you can sort of fit it neatly into the end of a short Pasteur pipette, and then you use a long Pasteur pipette to gently push that cotton ball to the bottom and then snub it into the end so that it's not likely to come out, and the end is then sealed so silica gel won't drain out. So the next thing we need to do is we need to actually fill the column with silica gel. So we don't fill it completely because we need to have some room for solvent, but somewhere between halfway and 2/3 full is a reasonable amount. So you can just dip the end of the clean column into silica gel and tap it down. You can see that you can fill the column usually in 2 or 3 dips into the silica gel container. Okay, and I'll show this to you now in just a second. Always important to recap the silica gel because its effectiveness is diminished by water, and it is a desiccant, so it will remove water from the air. So you can see now that this is our capillary column. It's about, I don't know, 2/3 full of silica gel. The next thing we need to do is equilibrate it. In order to equilibrate it, it'll be nice occasionally to be able to set the column down. So to set the column down, we get a test tube rack and a test tube. And what's going to hold our column when our hands aren't on it is just a test tube. So there's our column, and we need to equilibrate the silica gel with whatever running solvent that we have. Now, in order to get resolution in a chromatography column, you want to find a TLC solvent that has your desired compounds with an RF of about 0.2. An RF of about 0.2 is ideal for resolution, so your desired material has an RF of 0.2. That's the chromatography solvent that you would pick for a preparative chromatography. So I don't know exactly what it is for the compounds that I'm going to use. I'm just going to pick 10% ethyl acetate and hexane, and I'm going to now equilibrate this column. So you grab another small Pasteur pipette, and with that pipette you're going to fill that solvent reservoir that you left on top, and it doesn't have to be totally full. And then what you want to do is you want to push the solvent onto the silica gel. Now in silica gel chromatography, it's really important once that silica gel gets wet that it not get dry at any point. So you want to push the level of the solvent down to the level of the silica gel, but no further, and you want to do that repeatedly until the silica gel is saturated. And I have a little bit of air blowing through this tubing from the air in the wall, and I'm just going to use that rather than another Pasteur pipette bulb to save my arms from having to repeatedly force the solvent through the silica gel. This is a flash chromatography. And the reason why we call it flash is that we're forcing the solvent through the silica gel with air. You can also use nitrogen, but air is perfectly fine. So I'm not sure you can see on the video, but as this is going, the silica gel is getting a nice even gray color. And what I'm going to do is I'm going to push that solvent level down to within 1/2 millimeter of the top of the silica gel, but never let the solvent surface get below the surface of the silica gel. So now this chromatography column is equilibrated. What the solvent that moved through that, we know there's no compound in that, so we're going to set that aside, and we're going to get a new test tube out to hold up our column. And now what we need to do is load the column. At this stage, you would typically be loading a compound of interest, something you're trying to prepare. If it's a small quantity, like it's likely to be for a capillary or for a pipette column, you'd probably want to dissolve that compound in a solvent that is either the running solvent or a solvent that's lower in polarity than the running solvent. Today I'm going to use the same 2 compounds I used in my TLC video, And I'm just going to add a drop of each one to the top of the column and see if we can separate those two using the column. Again, this is just a demonstration, so I haven't optimized the polarity. So I'm just going to dip it in there and get a little bit. That's probably like I don't know, 5 milligrams or so, and I'm just going to add that first compound to the top of the chromatography column. So I'm done with that. I'm going to cap it up and get a fresh pipette so I don't contaminate the material. Get a fresh pipette, and now take a little sample of the other compound and add it to the chromatography column. Again, I'm not making any measurements. I've added between, I don't know, 5 to 8 milligrams of each of those compounds to the top of the column. And because the volumes are so low, you can see there's just a little layer of compound sitting on top. So what I'm going to do on top of the silica gel, so what I'm going to do is I'm just going to fill up with just a little bit of solvent, maybe like a half a centimeter of solvent on top of that. And what's likely to happen is in that half a centimeter of solvent, the compounds are likely to dissolve and be diffused. We want to load compounds in the minimal possible solvent. So I'm not going to fill it up completely. Now what I'm going to do is I'm going to take this solvent level and I'm going to do what's called drawing it down. I'm going to push just enough so that this solvent line comes down to the surface of the silica gel. That's going to force the compounds onto the silica gel. Okay, and then I'm going to repeat that to make sure that the compounds aren't getting diluted in the solvent. So I'm going to again add like a half a centimeter of solvent, and then I'm going to press that down. So now the compounds have been loaded onto the silica gel. So now we're actually going to run the column. The way you run a pipette column is you fill the solvent reservoir with solvent, then you press it down. And you can do it as many times as you like per tube. Usually I do 2 or 3 times per tube. So here I go. I'm going to run the column. I'm getting a little bit of solvent. I'm filling up the reservoir. And now I'm going to force that solvent down, but not past the surface of the silica gel. Just enough so that there's maybe a millimeter or 2 of solvent on top. And I'm going to do that, let's say 2 times per tube. And I will emphasize, I have not optimized the solvent polarity here. I haven't gotten the compounds, I haven't assured that the compounds have an RF of about 0.2. So I don't know how good the resolution will be of this separation. I'm just giving it a try, mainly just to show you the technique. So I've filled 1 tube, now I'm just going to repeat the same procedure on the next tube, and so on. Typically I run like one row of tubes, maybe between 10 and 16 tubes, and then I check the fractions to see which fractions may or may not have the compound in them. So I'm going to stop talking and I'm going to speed up the video so you don't have to sit through me running this column. Okay, I just completed my 10th fraction, so I'm going to put the column into another empty test tube and just let it sit in the back while I figure out whether the compound's already eluted in these first 10 fractions that I've collected. So I'm going to set my eluent, my running solvent, aside for a second, and now it's time to again do TLC. So here are my fractions. I'm going to put 10 spots onto this TLC plate, so it's going to be a bit wider than a TLC plate we might use for a reaction. And how wide really depends on how good you are at making small TLC spots. So again, I'm going to use 2 gentle swipes rather than 1 hard one to try to preserve the surface of the TLC plate. There's a bit of a jagged edge on all the sides that have been cut, so I'm going to go ahead and clean those surfaces up. And now I'm going to put 10 little spots on the bottom of that TLC plate, not touching the bottom, but close to the bottom. 1, 2, 3, 4, 5. I put a little line. 1, 2, 3, 4, 5. So I've got 10 little spots. I'll hold this up so you can see it. I've got 10 little spots on that TLC plate ready to run, or ready to load, I should say. So this is another instance where I'm going to stop talking for a little bit, and you can just watch me spot the TLC plates. What I'm doing is I'm using a TLC spotter, and I'll start by making sure that the edge is nice and square so I don't damage the TLC plate surface. I'm going to clear off the edge, and I can observe that that TLC plate or that TLC spotter has a nice perpendicular edge. It's not going to be jagged and scar the surface. And now what I'm going to do is I'm just going to spot each fraction, and you know, because we are in the Western world here, we're going to go from the left to the right in the TLC plate. So I'm just going to put the TLC spotter into the first fraction and just dab it a couple of times. Drain the rest of that material out. Oops, my TLC spotter broke when I dabbed it out, so I'm going to clean up the end again to make sure that it's square. And then I'm going to grab fraction number 2. And I'm going to repeat this for all of the fractions. The material that are that's in those fractions has been diluted with the solvent from the column, so you don't have to pre-dilute them like we did when we originally made when I showed you these compounds in my TLC video. I'm going to finish spotting it and stop talking for a minute. Okay, I've finished spotting a little sample of each of those fractions onto my TLC plate. And we know from the TLC video that one of those 2 compounds in this mixture is UV active. So let's go ahead and use the UV lamp to see if we can visualize that compound. And I'll have to be careful not to bump my fractions over as I move the UV lamp in here. So I'll get the TLC here. We haven't run it up the plate yet, so we expect to see some UV activity on some of the spots on the baseline. So the UV lamp is on, and hopefully what you can see is that it looks like in fractions 2 and more dark in 3 is that UV active compound. So it came out relatively early in the chromatography, probably a bit too early for ideal resolution. So if we had optimized this with the right solvent, having a solvent of lower polarity would have delayed those compounds' emergence from the column. So now what we're going to do is we're going to run this up using our TLC technique. So I have the same TLC chamber I used for the TLC video, and I'm just going to go ahead and open it back up. If you were careful about sealing the TLC chamber, then you can reuse it. And so this TLC chamber has the TLC eluent 25% ethyl acetate and hexanes, and all of the materials are going to get close to the top of the TLC plate. The solvent that I used to run the column was 10% ethyl acetate and hexane. So I've put it in there, the solvent's running up nice and even, and now I'm going to be quiet while it runs up, and I'll speed up the video so you don't have to wait. Again, what I'm watching for is the solvent front to get, say, about a ½ centimeter from the top of the plate. Okay, it looks like the TLC solvent is about, I don't know, a little less than a centimeter from the top of the plate, so I'm going to pull it out. I'll show you the TLC plate. Not quite to the top of the TLC. I'm going to draw a line so I could calculate the RF of those spots. Now let's go ahead and visualize using the UV lamp. So you can see that in fractions 2 and 3, in lanes 2 and 3, you can see there are two UV active spots, but then, you know, perhaps in fraction 4 and 5, that stuff has already finished coming out of the column. Okay, so It'll be hard for you to see this, but what I'm going to do is I'm going to put a little pencil circle around those UV active spots down here on the bench, so we can know where those are after we've burnt it. So I'll show you again. So I've just made a pencil circle around those two UV active spots. Alright, so now we're going to actually visualize the TLC plate by burning with phospholiptic acid. Just like we did last time, that stain seemed to work pretty well for those compounds. So here's my hot plate, here's my dabbing paper towel, and here's my TLC stain. So again, you dip the TLC plate up to the solvent front, but not much further. Try not to get the tweezers in the stain. I'm going to let that dry off for a second. It's always important to recap the TLC stain, because the TLC stain's in ethanol and it will slowly get more and more concentrated, and eventually it will be so concentrated it won't be of use to us. So I'm going to attempt to hold this up so you can have a better picture of its visualization by burning. So you can see that the solvent's evaporating. I don't know if you can see it, I can see it. And then we'll watch the spots come out as it continues to heat. Okay, so to do a little analysis on this TLC plate, you can see that the compound, or in lane 2, it looks like there's the UV active spot, and then there's another spot that wasn't UV active that eluded. In lane 3, it looks like there's the UV active spot trailing, and then a more polar spot that stains with phospholiptic acid. You always see the less polar spots come out first, and so that's kind of what we observe here. This column was run in a solvent that was too polar, so the compounds came out too fast. In order to get those compounds fully separated, we would have to decrease the polarity of the running solvent. I used 10%, perhaps 5% would have been a better choice. The way you would know that is you would run a preparative TLC until you find an RF of 0.2 for the solvent that you're using on a TLC plate. So to be clear, you get an RF of 0.2 on a TLC plate. That's ideal for separating that compound in on a preparative column. Although this separation didn't work perfectly, you can see that we did separate the less polar compound that stained with the PMA from the more polar compound that stained with the PMA. So those two compounds are in different fractions. The one we didn't resolve completely was the UV active one. The UV active compound is contaminating both of those fractions. So if we had used a lower polarity solvent, we might be able to resolve all of those compounds in the mixture. So in the final step of this process, what you would do is, assuming that you have identified what fractions contain which compounds, say we were interested in the compound that's in fraction 2 and compound that's in the fraction 3, we would take this fraction and then we would remove the solvent. And in this lab, typically what we're going to do to remove the solvent is we're going to put the entire fraction into a vessel, maybe a sample vial, and then we're going to put that sample vial onto a lightly warmed, not highly warm, but a slightly warm hot plate, and then using a pipette and a stream of nitrogen blow the solvent off. Typically the compounds of interest are less volatile than the solvent, so we can remove the solvent, and what we leave behind is a sample of whatever material was in that fraction. We would do that for this compound, and in fact one thing that we could do when working on a small scale like this is we could just blow nitrogen into this fraction tube and use the warmth of our hands to keep the tube from getting cold, remove all the solvent, and then we could actually take deuterated chloroform to dissolve that compound up, and we could put it directly into an NMR. That way we wouldn't have an extra piece of glassware to get in the way. If that compound was of interest, then we could transfer the NMR solvent into a vial and remove the NMR solvent by using a stream of nitrogen. Or alternatively, we could drop some of that NMR sample directly onto the IR and measure the infrared spectrum to help us identify what it is after we collected the NMR data. So that would be fraction 2, and if we were interested in what was in fraction 3, we would do the same procedure. Blow off all of the solvent. On this scale, it's just fine to do it in the test tube itself, using a stream of nitrogen gas from your hood, using the warmth of your hand to keep the tube from getting too cold. The reason why it's important to keep the tube from getting too cold is that as it gets cold, it will condense water from the air, so you'll get water in your sample. So it's best to use the warmth of your hand or the warmth from a sand bath or a lightly warmed hot plate to keep the tube at room temperature or a little bit warmer than room temperature as you're evaporating the solvent with nitrogen. If you didn't do that and you just use nitrogen, evaporation is an endothermic process and the sample will get colder and colder, and eventually you would see condensation and then frost on the outside of the tube, and obviously on the inside there would also be water condensing, since it would be also cold in there. So you would collect your compounds. The fractions that don't have anything of interest, that material would go into the organic solvent waste, and these test tubes are fairly affordable, and so we don't reuse them or wash them. So these small test tubes would go directly into the broken glass, as would the entire chromatography column and any other test tubes that you've used in the process after you've cleaned the solvent out of them. So that concludes this video.